Hey guys, this first video for chapter 17. The topic we're going to talk about is buffers. I believe the first 9 slides of the PowerPoint are fairly straightforward, so hopefully you can read through those and read the book and figure out the basic idea of what a buffer is and how it works. I'll talk a little bit about it here. So I'm picking up on slide 10. There's a problem on this slide that reads, a solution originally contains 0.5 molar acetic acid and 0.5 molar sodium acetate. That's what I have on the board. It gives you the volume of the solution is 50 milliliters. It gives me 2 concentrations, but it's because these 2 things are both present in the solution. Okay. First of all, I have 0.5 molar acetic acid. So that's the weak acid part of the buffer. Remember, buffer always is made up of 2 parts. It's a weak acid and its conjugate base, or it could be a weak base with conjugate acid. Okay. In this case, the weak acid is my primary component, but then I also have acetate ions present as well. Now, in the reading of the problem, it refers to 0.5 molar sodium acetate. Well, that's a ionic compound. When you dissolve it in water, the ions come apart. The sodium is just a spectator. Okay. Now, whenever they give you a mass of an ionic compound, if I'm going to take the mass and convert to moles, I do have to include the molecular weight in that conversion. But once it dissolves, the sodium is irrelevant. After that, we focus on the acetate portion. So this buffer solution in the beaker would contain some acetic acid and some acetate. That's what makes it a buffer. So in my buffer solution, I'm going to represent the acetic acid with the general formula HA. And I'm going to represent the acetate ions as the conjugate of HA, which is A minus. Okay, so those 2 things are coexisting in the solution. It's kind of important to realize that they're a conjugate acid-base pair, so in the solution I have an acid and a base both in there. Okay, now the job of a buffer is that it's going to hold a certain pH, whatever the pH of this solution is, it's going to try to maintain the pH as close to that value as it can. Okay, now why does it have to maintain the value? Is because usually we're going to dump in something into the solution that's either extremely acidic or basic that would want to change the pH from whatever it is. The buffer's job is to try to stop that from happening. Okay, so these are usually 2-part problems. Often on the test, I'm going to ask it as a 2-part problem, where first I'm going to want to know what's the pH of the buffer before I do anything to it. Okay, so part 1 of a problem. This is not specifically listed on the slide for slide 10, but I want to know what the pH of this buffer is. To find the pH of a buffer, there's an equation called the Henderson-Hasselbalch equation, where the pH of a buffer solution will equal the pKa, which if you look up the Ka of acetic acid, the pKa means take the negative log of the Ka value. Once you do that, the answer you get is the pKa value plus the log of the A minus over the HA concentration. Now, when we make a buffer, the pH of a buffer I can't make a buffer with acetic acid and acetate that has any pH I want. The pH of this buffer solution has to be reasonably close to the pKa value. Okay? Now, if I take the negative log of the Ka value for acetic acid, which the Ka is 1.8 times 10 to the minus 5, if I take the negative log of that, the pKa here is going to be 4.74. Occasionally people get 4.75 just depending on how they type in the Ka value. But that's my pKa. That's like the home value for an acetic acid acetate buffer. Okay? Now, I can adjust the pH of the buffer up or down a little bit by playing with the ratio of A minus over HA. If I have a buffer where A minus and HA had the same concentration as I do here, 0.5 molar acetic acid, 0.5 molar acetate, when they're the same, plug in a value over itself, that's going to drop out and become a 1. The log of 1 is 0, which means that whole term here drops out. And at that point, the pH of the solution will equal the pKa. So in a buffer that has equal concentrations of HA and A-, the pH will equal the pKa value. Okay, so this buffer that we have in our beaker would have a pH value of 4.74. So that's my starting point for this problem. The buffer starts out at that pH. All right, now, if I wanted to make a different buffer, again, separate from this problem, but just for discussion, if I change the ratio of A- to HA, that's going to cause the pH to go up or down from the pKa value. Okay? If I want to make the pH of the buffer a little higher, then I'm going to increase the A-, which is the basic part of the buffer. I'm going to increase the A- to be larger than HA. Okay? By doing that, and typically the rule of thumb that we use is the greatest ratio of A- to HA that we're allowed to use where the buffer will actually do its job is about a 10-to-1 ratio. If I increase the A- concentration to be 10 times more than HA, the log of 10 over 1, the log of 10 is 1. It's going to add one unit to the pKa value, which means the highest range a buffer will work is about 1 unit above the pKa. Alternatively, if I want to make the pH of the buffer lower, I can increase the amount of HA. Again, the limit that we're allowed to use is about a 10-to-1 ratio there. 10 times as much HA to 1 time A-. The log of 0.1 is going to be -1, which is going to lower the pKa by 1 unit. So essentially the range that this buffer will work is from about 3.74 to 5.74. That's the only range where an acetic acid sodium acetate buffer can be used effectively. Okay? The buffer that we have in this situation, though, specifically has a pH of 4.74 because we made equal parts. Okay? So that's my beginning of the problem. Now, if I use my buffer and I add something to this solution that is either an acid or a base, the buffer's job is to neutralize whatever it is I'm adding to get rid of it before the pH changes. Okay? Now the buffer won't be perfect. If I add something to the solution, the pH might change a little bit, but the buffer's job is to mitigate that addition as well as possible and try to keep the pH pretty close to what it was. Okay? So, it says in the problem on slide 10, I'm going to add 10 milliliters of 0.1 molar sodium hydroxide to this beaker. Okay? What's going to happen is if I add sodium hydroxide to my buffer, the buffer needs to neutralize it. How will it do that? Well, sodium hydroxide is a base. When I dump it in the beaker, there's an acid in there. The acid portion of the buffer is going to neutralize the sodium hydroxide. So that's going to be my HA, which stands for acetic acid. I need to write a reaction that represents the neutralization. So the sodium hydroxide is going to react with the acetic acid. And when they react, the OH and the H are going to form water. And then the sodium and the A- don't really come together because, again, that would form a aqueous ionic compound, which doesn't form. The sodium is actually a spectator. I could just ignore it and say this is hydroxide. And then the A- is going to form over here. So essentially the base is going to remove the hydrogen from the acetic acid and turn it into acetate. Okay? Now, this reaction is going to happen to the fullest extent that it can. Meaning this is not an equilibrium reaction. This is an acid-base neutralization. It will go to completion. So, instead of making an ice table, which is what we did in chapter 16, which represents the equilibrium between an acid and its conjugate base, for this one, I'm going to do another table that we call an IRF table, IRF. The I stands for the initial amounts, R stands for the amount that reacts, and that's the neutralization that occurs, and then F stands for the final amounts that I have when I finish. Okay, so IRF, if you want to sing it, Earth baby, it works. Okay, now in this table, another difference, an ice table always has to have molarities plugged into all the values. When I do an earth table, I either need the values to be moles or millimoles. Either one is fine as long as you're consistent throughout the problem. Okay, so on this one, since they gave me milliliters and molarities, if I multiply the molarity times the milliliters, it's going to give me millimoles. And that's what I'm going to do for all the positions. So my sodium hydroxide, I added 10 milliliters of 0.1 molar. 10 times 0.1 is going to give me 1 millimole of sodium hydroxide. The acetic acid, I have 50 milliliters and it's 0.5 molar. 50 times 0.5 is going to give me 25 millimoles of HA. One of my products is water, and again, when I do these things, water is just a solvent, so I'm not really worried about it. So I'm going to mark out the water line. But then the acetate, I do have acetate in the solution before the reaction starts. It's, again, 50 milliliters of 0.5 molar. 50 times 0.5, A minus, I have 25 millimoles. Okay, so that is the initial line. Those are the amounts that I have. My acid and base are going to neutralize fully for whichever one is the smaller number, meaning this is a limiting reagent problem. I have a little bit of base, I have a lot of acid. The base is going to fully get reacted, it's going to get neutralized, so I'm going to subtract 1. I'm going to neutralize all the base, so it goes to 0. It's a 1-to-1 reaction, so however much of this one I use, I'm going to have to use the same amount of HA. Minus 1, so it means it's going to leave me, my buffer is going to lose a little bit of the acetic acid. But typically the amount of the weak acid and the conjugate base in the buffer, they have to be larger than whatever you're going to add. That's related to the buffer capacity. If the amount of sodium hydroxide I add is too much for the buffer to handle, then the buffer won't work. Okay, so the amounts in the buffer have to be larger than the amounts that are being added of the foreign substance. So my HA goes from 25, loses 1, becomes 24 millimoles. I have to look also at my A minus though, because when I neutralize the HA, it doesn't just disappear. The sodium hydroxide, the base, removes a hydrogen from HA, so whatever HA I lose, it becomes A minus. So I lose 1 millimole of HA, I'm going to gain 1 millimole of A minus, so my A minus is going to end up being 26 millimoles. Okay, so after the addition of the sodium hydroxide, we get a shift in my buffer. I started out with equal amounts of HA and A minus. Well, I used a little HA, I gained a little A minus. These are the new numbers that I want to go now to the Henderson-Hasselbalch. If we want to find out what the new pH of the solution is, these are the two numbers I'm going to plug in the Henderson-Hasselbalch equation. Now, the Henderson-Hasselbalch equation technically should have molarities for the HA and the A minus values that are being plugged in, but since there's one value on top and bottom, and to change both of these back into molarity, I would be dividing by, my new volume would be 50 milliliters plus 10 of the NaOH. The new volume would be 60. Well, if I had to divide both numbers by 60, in a ratio, that step is actually unnecessary. So when I finish the earth table, I can take these two numbers, plug them back into the Henderson-Hasselbalch equation, and then solve for the pH. So the equation is going to look like the pH of the new solution equals the pKa, which we already know is 4.74, plus the log. And when I do the log, it's always the A minus over the HA, so it's going to be 26 over 24. And if you solve for it, what we would find is that the pH of the solution is going to be a little bit higher than 4.79. Okay? But if we comparatively took a beaker of water and added the same amount of sodium hydroxide, the pH would have gone up by several units, like from a pH of 7 to a pH of probably near 12. That would have been a huge change in pH if the buffer wasn't present. Because the buffer is present in this problem, the pH probably only goes up by about 1/10 of a pH unit, or maybe even less than that. You guys can figure that out yourselves. So that's how buffer problems work.